Hello everyone, myself Naida Taranam. So today we'll continue with the module 2 in the Verilog HDL, that is basic concepts in module 2 module and ports, session 6. These are the contents. These are the contents what we'll be studying here, that is the port connection rules, connecting ports to the external signals and the hierarchical names. This is a block which is going to explain the port connection rules. Here, the port connection rules consist of two units. One unit is that which is connecting to the internal to the module, and the other that is connecting to the external of the module. So two units, one unit that is internal to the module and the another that is external to the module. The internal and external units are connected. These are the rules that is governing the port connections when the modules are instantiated with the other modules. So the inputs, internally input port must always be of internally the input ports must always be of type net, and externally the input port can be connected to a variable which is a resistor or net. Coming on to the outputs, internally output port can be either of type resistor or net. Externally output must always be connected to a net. They cannot be connected to a resistor. They must always be connected to a net. In-out. Coming on to the in-outs. Internally in-out ports must always be of type net, and externally in-out ports must always be connected to a net itself. Then we have a width matching. It is illegal to connect internal and external ports of different sizes when making internal module ports connections. If such has been done when the width is not been matching, then a warning has been typically issued that the width do not match. And then unconnected ports. Coming on to the unconnected ports here, Verilog allows ports to remain unconnected. So this is an example. This is an example wherein we have taken an example of a full 4-bit full adder with a module name, the component name wherein it has been taken as FA0, wherein we have 4 bits of sum, 1 bit of Cout, 4 bits of A, 4 bit of B and single bit of C in. Here you can see Cout is not been connected. So in such cases unconnected ports can be left without entering the information. This is the Cout is not entered here, so it has been acting as an output port Cout, which is unconnected ports. This is an example for a port connection rules wherein we are taking a 4-bit full adder. This is a module and which is the top level stimulus which is trying to instantiate a 4-bit full adder module. Here we have taken, that is the module top. Module top is a top level stimulus which is not having the port list. So there are no pins entering inside nor the pins going outside this top level stimulus. So that is why the port list is not been written, that is module top then terminated with a semicolon. And here we are trying to declare the ports. So whatever the input ports what we have, that is the input ports A, B, C underscore in are been declared as resistors, and A and B are been declared as 4 bits of input pins, and C is a single input. So that is why resistor within the square brackets 3 down to 0 A comma B and then terminated with the semicolon, because A and B are of 4 bits of input and resistor C is a single bit of information. So in the top level stimulus all the inputs are been declared as resistors. So that is what is the port connection rules we had. That is all the inputs that is been fed to the input internally, from externally we are connecting it to the input. So the resistor is been declared in the top level block. We have this resistor. So it has been declared as a resistor A comma B which is of 4 bits. So 3 down to 0 A comma B, and a single bit of input register C underscore in. And here we have declared, as we have seen that in the port connection rules, that is the pins coming out of the output that should be connected externally should be net, wherein we will be rating it as a wires. The other name for the net is wire. So it has to be declared as a wire, but here it has been declared as a resistor. Resistor 3 down to 0 sum, then terminated with the semicolon, and the C out is an output that is going from the that is output pin which is going to connect to the externally to the other module. So wherein we'll be trying to declare it as a wire C underscore out and then terminate it with the semicolon. And this is what is a instantiation it has been doing here. This is what is the instantiation, what it is trying to do for the full add 4. And the module name what we have taken the full add for, this is the module name what we have taken the full add for, and this is the label given to the block. And these are the ports sum comma C underscore out comma A comma B comma C in, and then close the parenthesis and then terminate it with a semicolon. This statement is going to give us an illegal connection, because here the output should be of type wire. It has been declared as a resistor, as we have seen it in the port connection rules. And then we'll be trying to write the stimulus block, the functionality whatever we want, we'll be trying to write in the this part of the portion, and then finally end up with the end module. And then connecting the ports to the external signals in two ways, connecting it by the order list or connecting the ports by the port names. These are the two methods wherein how you can connect the ports to the external signals, by order list or by the name. First we will be seeing the connecting the ports to the external signals by the order list with an example here. So this is what is a order list, that is sum comma C underscore out. This how we will be trying to write the first the module followed by the module name full add 4, and these are the port list what we have sum C underscore out at the output. So first we'll be trying to write the outputs followed by the inputs A comma B comma C underscore in, and then close the parenthesis and then terminate it with a semicolon. First the outputs are been written, that is sum comma C underscore out followed by the inputs A comma B comma C underscore in. All these variables are been separated by the commas. Within the parenthesis we are writing and then terminating with a semicolon. So in the next part here we are trying to declare, as a port list has been assigned, as a port list has been clear, we are going to do the port declaration. So sum is of out type, C out is also an out type. So sum is a 4-bit of information, so we are trying to write it as output 3 down to 0 sum. It is a vector which is consisting of 4 bits of information, and the carry what we will be having for the 4-bit full adder is a single bit of information, so it is only written as output C underscore C out and then terminated with a semicolon here. And then A and B are of 4 bits, so that is why we are trying to declare the port as input 3 down to 0 A comma B and then terminate it with a semicolon. And C in is a single bit of information as an input, so input C underscore in then terminate it with a semicolon, and the functionality has been written here and then finally ended up with the end module statement. This is what is a main module. Now trying to write the top level stimulus by the order list, that is you are trying to connect the ports to the external signal. So this what we had, this part has been written in the main module. Now we will be trying to write the top level stimulus, that is module top. For this module top we have taken the pins as A, B, C and uppercase variables A, B, C underscore in as inputs, sum and C underscore out are the outputs. As these are the pins that has been coming from the external signals entering inside the internally connected, externally from the external it is connected to the internally modules. So here these has to be declared as a resistors. A, B, C in are been declared as resistors, and sum and C out should be declared as wires. That is what is a port connection rules. So it should be placed in the same order. So that is how we are rating it as resistor 3 down to 0 A comma B, then terminate it with the semicolon. Resistor C underscore in, terminate it with the semicolon, and these outputs are been declared as wires connecting to the external signals. So wire 3 down to 0 sum, then terminate it with semicolon, wire C underscore out, terminate it with a semicolon. Now this top level stimulus is going to instantiate a full adder, that is full add 4. So full add, it is trying to instantiate the full add, and whatever the instantiate, that is a component name you all want, you all can give it. So FA and hyphen ordered is a name given to this component, and the variables what we are trying to write, that is the port what we are trying to write here, should be in the same order what we have written it to the here in this module. So whatever the module name we have taken, the port list what it will be occurring here should be in the same order of that of the variables what you have written it in the port list that has been declared in the main port. So this is what is known as a connecting by order list. The sum has been connected to the sum of this, that is this sum has been connected to the sum. C underscore out has been connected to the main module C underscore out, and then A has been connected internally to A, and the capital B has been connected to the lowercase b. C underscore in has been connected to the C in. So it should be in the same order how it has been occurring it in the main program. So this is what connecting by the order list, and then trying to write the whatever the stimulus information, that is a functionality we want, we'll be writing here in this portion, and then finally end up with the end model. This is what is a connecting by the order list. But here there is a problem that as a connectivity, as the system goes on, that is a circuitry goes on increasing, that is the number of ports increases, and it is very difficult to remember the order list, connecting by the order list. So it is very difficult to connect it, remember the order list. So that is why we will be going by, that is connecting port by names. That is for larger design where modules have many ports, remembering the order of the port in the module definition is very difficult. It is impractical, and the possibilities of error. So in that cases we will be going on by the port names. So here, that is, this is the main program what we had, the module name, module followed by the module name, that is this full adder, full add 4, sum comma C underscore out, A comma B comma C underscore in. This is the port list what we have written it in the main program within the parenthesis, and then terminate it with a semicolon. And this top level stimulus is going to instantiate a full add 4, and this is the component name, what is a module name what we want to connect to signals by the name, port name. And this is what we will not be remembering the order of the ports, so we will be trying to connect it by the port name. So the port what we have, that is the syntax we will be having here, the syntax here, that is dot C underscore C out. This is what is a internal port, and the external port within the parenthesis C underscore out, comma, then this is the internal port what we have, that is the dot sum followed by the external port connection, dot sum, and then followed by the external port connection. Then same dot B is the internal port, and the external port is within the parenthesis. Same with the dot underscore C is going to tell the internal port, and the external port is the external signal what we have, that is C underscore in. This is the internal port, that is dot A, and the external signal is capital A within the parenthesis. Close the brackets and then terminate it. So when we have the larger designs, it is very difficult to remember the order of the ports. So in such cases, we will be going for the connecting ports by the names, which is trying to remove the errors. Next, we have the hierarchical names. So in this hierarchical names, so we have already described in the earlier first module that Verilog supports a hierarchical design methodology. Every module instance signals or the variables is defined with an identifier. A particular identifier has a unique name, and then hierarchical name referencing allows us to denote every identifier in the design hierarchy with a unique name. So the hierarchical names are been separated by the dots for each level of hierarchy. This is what is the syntax what we have, that is a top level module. Then the instance which is trying to instantiate the top level module is trying to instantiate the instantiator name, and then the identifiers for those instantiated. It has been separated by the dot. It has been separated by dots. The list of identifiers have been separated by the dots. So here we have taken an example of an SR latch, wherein the top level stimulus has been instantiating the SR latch, and then SR latch has been in turn instantiating the two NAND gates. So this is what is the top level stimulus, wherein the outputs are Q bar, and the inputs are set and reset. So this is trying to have the variables, that is the identifiers Q comma Q bar comma set comma reset. These are the identifiers, the variables that are been identifiers of the stimulus. And this stimulus in instantiating the SR latch. So which is what is having the label M1 is a label given for the SR latch, and the SR latch has been instantiating the two NAND gates. So two NAND gates what we have, N1 and N2, and then the outputs and the inputs for this SR latch with the label M1, we have Q, Q bar and S and R. So Q comma Q bar, S and R are the signals that is been for the SR latch, the identifiers for the SR latch. Now we'll try to write the hierarchical names for this. So first we have the stimulus. So this is what is the syntax what we have, how we'll be writing the top level module name, then the instance name, then the identifier which has been separated by the dots. The top level module name, that is the stimulus, and then the instance, that is the identifiers coming out, identifiers for this top level module is Q. So it has been separated by a dot, stimulus dot Q, stimulus dot Q bar, stimulus dot set, and stimulus dot reset. This is the identifiers for the top level stimulus, and this stimulus is instantiating the SR latch with the label M1. So that is what stimulus dot M1, and this M1 is having the identifiers Q, Q bar, S and R. So M1 comma M1 dot Q, that is stimulus dot M1 dot Q, stimulus dot M1 dot Q bar, stimulus dot M1 dot S, and stimulus dot M1 dot R. And this SR latch is in turn instantiating the two NAND gates. So that is what we have, that is stimulus dot N1 and stimulus dot N2. So this is what how we give the hierarchical names. Thank you.